Okay, so here's chapter 10 homework starting from 16. In which of the following structures does central atom have a formal charge of +2? Now you guys know how to calculate the formal charge. How is it? First find the group number and then you subtract the number of bonds and electrons on the central atom. Now for the aluminum here, we always look at the central atom. Aluminum group number 3. Okay, and then it has 4 bonds, so 3 minus 4 minus 1. What about oxygen? Group number 6 minus number of bonds 3 and lone electrons 2. 6 minus 5, that is plus 1. And then the next one, sulfur. What's the group number for the sulfur? Sulfur is 6. And then the number of electrons, not the electron, number of bonds, 6 minus 6, 0. And then the next one, group number for sulfur is 6 minus number of bonds, 4. There are no electrons, so plus 2. So we found the one that has formal charge plus 2, which is this structure. Okay. And then we have another one. Let's look at the beryllium chloride. So the beryllium group number is 3, number of bonds 2, 3 minus 2, 1. So that's not the correct one either. Okay, great. 17. In which one of the following the central atom, an exception to the octet rule, meaning the central atom has either less than 8 or more than 8. Now BH4. We talk about boron can be electron deficient atom. It can have 6. But in this BH4 molecule, how many electrons boron has? Shared electrons? 8. If you draw BH4, it would be like this. Right? So it is not an exception to the octet rule because boron has 8 shared valence electrons. And ammonia, if you draw ammonia, ammonia is like this. Right? It has 8 valence electrons. Ammonia is also obeys the octet rule. Same thing for iodine. Ammonium ion would be you have 4 hydrogens on nitrogen having 4 bonds, so 8 valence electrons. But for SF6, if you look at that, there are 6 fluorine atoms on sulfur. Each will have a single bond to fluorine, so 2 times 6 is 12. So the exception is SF6. Okay. And then the next one, which of the following atoms can expand its valence shell when bonding? And then how do we get the expanded valence shells? If they have d electrons, empty d electrons. So the d orbital started in period 3. Period 3, non-metals. So the elements, period 3, non-metals and below of that in the periodic table can have an expanded valence shell. So oxygen is in period 2. So the oxygen cannot have expanded valence shell. Okay. So carbon is also in period 2. Phosphorus in period 3, non-metal, which can have an expanded valence shell. But the nitrogen again in period 2, nitrogen cannot, and aluminum in period 3, but it's not a non-metal, so it cannot have expanded valence shell. Okay, so it's phosphorus is the correct answer. According to Vesper theory, molecule with the general formula AX2. AX2 meaning you have a central atom and then you have 2 atoms. So then the best way that the 2 X atoms can be far apart from the central atom is having a linear molecular shape. So the correct answer is linear. According to Vesper theory, molecule with the general formula AX4 will have a molecular shape. AX4 means there are 4 atoms. A in the center, and then you have another X, 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 X. Now on the paper, we can draw it as a square planar molecule, 90 degrees bond angle. But you know, in reality, it's not the shape. The shape is going to be tetrahedral, meaning it would be something like this. You have a and then you have X atom, and then X, X, X. Over here. So that is having each bond angle 109.5. 109.5 bond angle, having a tetrahedral electronic and molecular shape. It's going to be tetrahedral. Okay. For AX4 will have a tetrahedral molecular shape. And 21, according to Vesper theory, AX2E2 will have a molecular shape. Now here you have a central atom, and then you have two atoms attached to the central atom, and there are two lone pairs. These are your lone pairs. E represent lone pairs. X represent atoms. Now, how many electron groups do we have on this central atom? Remember, the electron groups will define the electronic geometry, and from that we can define the molecular shape or the molecular geometry. Now in this molecule on A there are 4 electron groups. Electron groups could be your single bonds. There's 1 and 1, 2 single bonds, and then you have 2 lone pairs. So that is 4 electron groups. And your electron groups could be a single bond, double bond considered one group, a triple bond considered one group, and a lone pair also considered one group. So this one has 4 electron groups. When you have 4 electron groups, the tetrahedral is the electronic geometry. But the molecular shape will define by how the atoms are placed in the electronic geometry. In the electronic geometry, we can see that the two atoms, X and X, but the lone pairs is just there in the position of the tetrahedron, but they do not contribute to the molecular shape. Okay, so this shape will become then bent shape, not linear, bent shape. Okay, because it has to come from tetrahedral electronic geometry. And then number 22, what is the molecular shape? Now in this one, we are given the Lewis structure, so you don't have to draw it. Now here you're going to look at your central atom. Always when you're looking at the shape, you have to look at the central atom and see how many electron groups are there on the central atom. We have one single bond and we have a one triple bond. Remember, triple bond is considered as one group, so there are two groups. So the best way that they can stay far apart without having any steric hindrance is going to be linear shape. So there would be linear. And then the next one, again, what is the shape? Here you have, we're going to look at again the central atom. Nitrogen is going to be your central atom. So here, how many electron groups are there? We have a single bond considered one group, double bond considered one group, a triple bond considered a lone pair considered a one group on nitrogen. So there are 3 electron groups. So what is the electronic geometry? If you have 3 electron groups, electronic geometry would be, so you have lone pair here, and then you have chlorine, and then you have oxygen. Electronic geometry would be trigonal planar. Correct? Trigonal planar. But since it has a lone pair, this will take the shape of a bent molecule for the molecular geometry, molecular shape. So the shape of the molecule is going to be bent because you only consider how the shape going to be. The shape is like this. You see? It's bent molecule. So the correct structure, the answer is bent. It's coming from the trigonal planar electronic geometry, but the shape of the molecule is going to be bent since there is a lone pair. Okay. Next one, what is the molecular shape of BCl3 as predicted by the Vesper theory? Now for this one, you will have to draw the Lewis structure, BCl3. If you draw the Lewis structure, so boron will be in the center. Okay, and then you're going to have 3 chlorine, 2 light. boron, chlorine, chlorine, chlorine. You will have your lone electrons on chlorine, lone pairs. So this is going to be the BCl3 Lewis structure, and it's asking what's the molecular shape. So there are no lone pairs on boron, so this one will have a trigonal planar electronic geometry as well as trigonal planar molecular shape. So the correct answer is going to be trigonal planar. Okay. And then the next one. What is the molecular symmetry around the carbon in CCl2CH2 as predicted by the Vesper theory? Molecular symmetry. In other words, it's asking what's the shape. So CCl2CH2, so the carbon will be in the center. You have 2 chlorine and then CCl2CH2. So that is CCl2. And then this, let me redraw it. Change this bond. CCl2, and then you have 2 hydrogens on the other one. Okay, so you can count the number of electrons, valence electrons and all that when you are drawing the Lewis structure, which you know how to do. And then, so you will realize now when you draw the skeleton structure, carbon having 6 electrons. And we're going to have a double bond between the 2 carbons. Okay. Okay. Now if you consider this one carbon, how many electron groups are there on that carbon? How many electron groups? So this is 1 electron group, 2 and 3. So there are 3 electron groups. If you have 3 electron groups surrounding the central atom, and they all are bonds, what should be the electronic geometry? Trigonal planar, as well as the molecular shape going to be trigonal planar because it does not have any lone pairs. Same thing for the carbon, the other carbon. This, if you look at this carbon, 1 electron group, 2 electron group, 3 electron groups. So 3 electron groups. So that will take trigonal planar electronic geometry. So both carbons have 3 electron groups, so both of them are trigonal planar since there are no lone pairs on carbons. So it's going to be trigonal planar electronic geometry. Okay, so 23 bent C. And then the next one, did we do? Yeah, 25, yeah, 26. What is the molecular shape of ClO3F? So the structure is drawn here, which is a good thing. You don't have to draw that. So again, so what you need to do is you're going to look at how many electron groups are on the central atom to find out the shape. So what are the electron groups? Single bond considered 1 group, double bond 1 group, triple bond 1 group, a lone pair 1 group. So this one has 1, 2, 3, 4. If you have 4 electron groups, so then the electronic geometry is going to be tetrahedral. So that is tetrahedral. Next one, what is the molecular shape of NH2Cl? NH2Cl, now for this one you have to draw the Lewis structure. NH2Cl, you will have lone pair on nitrogen. It's asking what is the molecular shape. Now, the molecular shape has to come from your electronic shape, electronic geometry. But then when you consider the molecular shape, you will not consider the placement of the lone pair. It's there, but you only look at the placement of the atoms. Now, this one has how many electron groups? 4 electron groups. If it is 4 electron groups, the electronic geometry has to be tetrahedral, meaning you have a nitrogen here, and then in the tetrahedron, you on one place you have a lone pair, and then you have the other 3 hydrogens like this. Okay, now what is the shape? Shape of the molecule will come based on the atom placement. So how does the shape going to be in this one? It's going to be, it will take the form of a pyramid, and this is a trigonal pyramidal. Not trigonal plane because it's a coming from the tetrahedral electronic geometry. So this one, C, is trigonal pyramidal molecular shape. Okay. And then the next one, what is the shape of XeO2F2? Again, this one we are given the Lewis structure. So we can look at how many electron groups are there. How many do you see here? I see 1, 2, 3, 4, 5 electron groups. Okay, there are 5 electron groups. Everybody see these 5 electron groups? Do you want me to circle it? So this single bond is a 1 electron group. This is 1 electron group. Okay, and this is another electron group, 2, 3, 4, 5. So there are 5 electron groups. If you have 5 electron groups, what is the electronic geometry? Remember we learned about that. Let's say you have your central atom here, A. Okay, so you can have 2 bonds, axial, X, X. And then you can have 3 bonds, equatorial, like this. So this one is similar to having 2 pyramids. And you can consider as trigonal bipyramidal. Electronic geometry is trigonal bipyramidal electronic geometry. And then, but in this one, out of the 5 electron groups, one is a lone pair. One group is a lone pair. So instead of X, now you have a lone pair. Okay, if you have a lone pair also takes some space. How does the shape of the molecule look like? If you rotate this one, you can consider something like that. A is here, X, 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 and a lone pair. How does it look like? It looks like something you use when you were a little kid, right? That look like a seesaw. So the correct molecular shape is going to be seesaw. 5 electron groups with 1 lone pair. That's a seesaw molecular shape. And then the number 29. What is the molecular shape of SCl3F as predicted by the Vesper theory? Now for this one, we need to draw the Lewis structure for SCl3F. Okay. So sulfur is going to be in the center. 3 chlorine, and then you're going to be having 1 F. And then we will have a lone pair on the sulfur. So let's count. Sulfur group number 6. Chlorine, 3 chlorine. 7 times 3, 21. 1 fluorine, 7. 28. 36. So 36 is the total number of valence electrons. So we can put lone pairs. 2, 4, 6. And 12 here, 18, 24, right? So we put 24 valence electrons out of the 36. For the skeleton we use 2, 4, 6, 8. 28 minus 24, 4 left. Okay, so we have 36 valence electrons. Sulfur is 6, fluorine 28, 28, 30, 34, not 36, 36, not 36, I did a mistake. So it has to be 34 here, right? You didn't tell me. You just wait until I do the mistake. So 34. Yes, that's correct. So I was wondering something's wrong right there. So that's going to be then 26. 26 minus 24. will be 2, and that 2 will go on sulfur. Okay, so now that's the correct Lewis structure for SCl3F, and there are 5 electron groups on sulfur. Okay, and then we have 4 bonds and 1 lone pair. So if you have 5 electron groups, the electronic geometry would be trigonal bipyramidal with the 1 lone pair on the equatorial position. It will give us a seesaw molecular shape, just like the previous one. Okay, and number 36. So number 36 is going to be, what is the molecular shape? Okay, so the structure is given to us, easy, right? So you just have to see how many lone pairs and how many bonds on the central atom. We don't have any lone pairs, so we have only bonds. There are 6 bonds. So when you have 6 bonds, what is the shape of the molecule? That would be octahedral. Easy. Octahedral. And then the number 31, what is the molecular shape of ClF4 minus? Again, you have to draw the Lewis structure for this one, ClF4 minus. Now the halogen, chlorine, is going to be in the center here. Okay, let's look at the valence electrons. All of these are halogens. There are 5 halogens. So 5 times 7, 35. Now let's do one at a time. It's okay. Chlorine, 7. There are 4 fluorides. 4 into 7, 28, plus 7, 35. And this is a negatively charged ion. So if it is a negative, meaning you have gained an electron. Remember how the anions are formed? By gaining an electron. So you're going to be adding 1 if you have a negative ion. So 36. So there are 36 valence electrons. So chlorine going to be in the center, and they are going to be 4 fluorides. Now we used 8 for the skeleton, so 28 left, and then you put your lone pairs. That is 6 times 4, no, yeah, 6 times 4, 24, 24, and then you are left with 4 electrons, and those 4 electrons you're going to put on the central atom, chloride. So now we look at our central atom. There are 4 bonds and 2 lone pairs. So the total number of electron groups are going to be 6. When you have 6 electron groups, you will have octahedral electronic geometry. Okay, so Cl in the center. So you have 4 groups. 1, 2, 3, 4. Fluorine, 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 but you have 2 lone pairs, right? So it's coming from the octahedral electronic geometry. Since you have 2 lone pairs, it will take the 2 opposite sides, giving you a square planar. Yes, square planar. Square planar molecular shape. Okay, and then the number 32. Use Vesper theory to predict the electron group arrangement. Electron group arrangement. Now it's not asking about the molecular shape. It's asking electron group arrangement around iodine IF2 minus. Again, you have to draw the structure. Okay, so IF2 minus. Let's count the number of electrons. Iodine is 7. Okay, group number. There are 2 fluorides. 2 times 7, 14. And then the 14 plus 7 is 21. So the total number of valence electrons 21. It's IF2 minus 1. This is supposed to be like this, IF2 minus, not minus there. Okay, so then you add 1 electron to this one, if you have a negative charge. Now we have total number of electrons 22. Okay, now we will put that 22 in our structure. I going to be in the center, F, F. Out of the 22, we use 4 for the bonds, so we are left with 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You use 12 for the valence electrons, terminal electrons for the fluorine. So how many left? 6 left. So for that 6, you're going to put those as lone pairs, 3 lone pairs on iodine. Now it is asking what is the electron group arrangement. Electron group arrangement. Now how many electron groups are on iodine? This is one group. 1, 2, 3, 4, 5. 5 groups. When you have 5 electron groups, that is trigonal bipyramidal. If it is asked what is the shape of the molecule, then it would be linear. Okay. So 5 electron groups is going to be trigonal bipyramidal. For 31, I circled 2. Okay, so the next one. What was the answer for 31 we came up with? I think I gave you the answer. I forgot what it is, but I gave you the answer for that. Okay, so the next one. 33. Predict the smallest actual bond angle in BRF3 using the Vesper theory. BRF3. Again, we have to draw the Lewis structure for BRF3. So when you draw the Lewis structure, so bromine is going to be 7, and then the 3F, 21 plus 7, 28. Okay, so the total number of valence electrons 28. You put bromine in the center, fluorine, fluorine, fluorine. So out of the 28, you use 6 for the skeleton. So you are left with 22. So for that you put here 18, 6, 12, 18, 18, and then how many more left? 4. So that 4, you put 2 lone pairs on bromine. Predict the smallest actual bond angle in BRF3. Now Br, the bromine in the center, has 5 electron groups. If you have 5 electron groups, the electronic geometry would be trigonal bipyramidal. And in the trigonal bipyramidal, if you want to put a lone pair, normally we put it in the equatorial position, where it is the square planar, not the square, trigonal planar arrangement. Okay, so this is how now if you have bromine here, and then we can see that these are the axial bonds, these are the equatorial bonds. Okay, there are 3 atoms and they are fluorine. Okay, so the fluorine will be here, and then the 2 lone pairs going to be here in the equatorial position. Okay, now it's asking about the bond angle. Now the bond angle between the atoms are going to be, what do you think is the bond angle? Now between these two bonds, bond angle is 120. Between these two, 120. These two, 120. Okay, but between these they are going to be 90. So since there is a lone pair, two lone pairs, they repel more. These two repel more, making the two fluorine bonds become more bent towards this side, making the bond angle less than 90. Okay, so the bond angles are going to be then less than 90. Okay, number 34. Which of the following has no net dipole moment? Again, for this one, you will also have to draw the Lewis structures and see if the bond polarities will get cancelled by looking at the shape of the molecule. So you have to draw all 5 Lewis structures, and then you will find TeO3 does not have a net dipole moment. TeO3. And then which one of the following has a zero dipole moment? Again, similar to the previous one, you will have to draw all the structures of the Lewis structures of the molecules and see if the bond polarities will get cancelled. For CS2, you will find that when you draw, the molecule would be something like this. So carbon sulfur does have a polar bonds. There is sulfur is going to be more polar, but their polarities are equal and opposite. So the bond polarities get cancelled and will become zero dipole moment. Okay. Okay then. That's about it. I'll talk to you later.